Hey everyone, and welcome to today's Explainer. We're diving deep into the operational logic of transport layer protocols and TCP header math. You know, if you've ever stared at network layers and just wondered, how on earth does all this data flow without instantly collapsing into total chaos? Or, hey, maybe you're just prepping for a major computer science exam. Well, you're exactly where you need to be. We're going to take those abstract, kind of intimidating formulas, turn them into simple math, and hand you the structural keys to understanding how the internet literally holds itself together.
Okay, let's quickly check out our roadmap for today. We're going to hit window sizes and sequence numbers, crack some ARQ window formulas, break down the anatomy of TCP headers, figure out how to calculate TCP header length, and then wrap things up with some real-world exam spotlights.
All right, let's jump right in. Section 1, window sizes and sequence numbers.
I need you to lock these two key variables into your memory right now because they are the absolute foundation for everything else we're going to talk about today. First, we have the transmit window. We call that N. This is the absolute maximum number of frames a sender is allowed to just push out onto the network without waiting around for an acknowledgement. On the flip side, we have the receive window, or HEM. This is exactly how many frames the receiver is actually prepared to accept and buffer. Without these strict mathematical windows, a fast sender would completely overwhelm a slow receiver and you just get massive data loss.
And that brings us to our very first crucial formula. To stop data loss in a noisy channel and to make sure a delayed acknowledgement doesn't accidentally trick the receiver into thinking a duplicate frame is a brand new one, the total number of distinct sequence numbers absolutely must equal the transmit window size plus the receive window size. It's that straightforward. Total distinct sequences equals N plus M. It's honestly this incredibly elegant, powerful rule of network design.
So you know the formula in theory, right? But how exactly does this N plus M logic actually show up when you're sitting in a high-stakes exam environment? Well, let's test this concept right now and see exactly how examiners are going to try to trick you.
Let's tackle this 2-mark question from the GATE IT 2004 exam. It's asking, in a sliding window ARQ scheme with a transmitter window of N and a receiver window of M, what's the minimum number of distinct sequence numbers required for it to operate correctly? Now, if you didn't know our foundational rule, you might guess, the max of M and N, or maybe M times N. But because we just went over that simple operational logic, you can crack this instantly. The answer is definitively C, M plus N.
Moving right along, Section 2, cracking ARQ window formulas.
So the really crucial point here is memorizing how our N plus M formula adapts to the strict rules of different protocols. In a basic sliding window protocol, the distinct sequences are just N. But think about go back in ARQ. It strictly locks the receiver window, M, at exactly 1. So N plus M simply becomes N plus 1. Then you've got selective repeat ARQ, which demands that the receiver window be exactly equal to the transmit window for it to work. If M equals N, then N plus N becomes N plus N, or 2N. Getting this logic down gives you the master key for literally any sequence protocol question they can throw at you.
But here's where we have to add a layer of practical reality. Computers, right? They don't just use abstract numbers. They use bits. When we introduce our next key variable, using k bits for the sequence number field in our frame header, our total sequence pool gets restricted. It's capped at 2 to the power of k. And because of that, the valid sequence range is exactly 0 up to 2 to the power of k minus 1. Since our total pool of numbers is now rigidly capped by binary math, our maximum window limits absolutely have to change. Let's break down how the maximum transmit window size, N, scales when we use those k bits. For the standard sliding window, N is simply 2 to the power of k. Easy enough. For go back N, because we need that one distinct sequence reserved for the receiver, N becomes 2 to the power of k, all minus 1. But pay super close attention to selective repeat ARQ. Because the sequence space has to be perfectly split right down the middle between the sender and receiver, remember that 2N rule, the formula for selective repeat actually shrinks the maximum transmit window size to 2 to the power of k minus 1, up in the exponent. It literally cuts the available transmit window right in half. That specific exponential shift, that is a favorite trap for test makers, no joke. Let's put that 2 to the power of k minus 1 logic to the test with another exam spotlight. Consider this GATE CS 2005 question. It's asking for the maximum window size for data transmission using the, quote, selective reject protocol with n-bit frame sequence numbers. The brilliant trick here? It's basically a vocabulary test. Selective reject is just another name for selective repeat. The moment you realize that, you instantly bypass the trap of option A, which is your standard sliding window, and option C, which is go back in. You just know the answer has to be B, 2 to the power of n minus 1.
All right, let's shift gears. Section 3, Anatomy of TCP Headers.
Before we get in there and dissect the really intricate details of the header itself, we need to visualize the big picture. A TCP segment is honestly just a data package. It has two main parts: a variable-sized TCP header block, which ranges strictly from 20 to 60 bytes, and that's immediately followed by your actual data payload. That header is basically the command center. It's telling the network exactly how to handle your payload.
If we break down the standard rows inside that TCP header, you'll see each row is exactly 32 bits wide. The 32-bit sequence number lives right there in the second row, acting as the tracker for all our data bytes. Right below that, we have the acknowledgement number. And then, this is absolutely crucial, in the fourth row we have this tiny little 4-bit field labeled HLN, which stands for header length. That tiny 4-bit field actually dictates the entire size of our command center.
Which brings us to Section 4, Calculating TCP Header Length. Now, the most common mistake I see students make when studying TCP isn't even the complex math. It's a super simple unit confusion. You've got to clearly distinguish between words and bytes. In the context of a TCP header, a word represents exactly 32 bits, which, as we just established, is the width of one standard row. Since 8 bits make a byte, a 32-bit word is always going to be exactly 4 bytes. Just burn this rule into your brain. One word equals exactly 4 bytes.
Let's see how that rule builds our calculation process. Finding the total size of the TCP header in bytes takes 3 really simple steps. First up, you identify the binary value inside that 4-bit HLN field and just convert it to a normal decimal integer. Second, you treat that integer as the number of words or rows in the header. Third, because every single word is 4 bytes, you just take that HLN value and multiply it by 4. That is it. HLN times 4 equals your total bytes.
Let's map out the absolute limits of this logic. Since HLN is a 4-bit unsigned integer, its maximum binary value is all ones, which gives us 15 in decimal. So, the operational logic dictates that our header absolutely maxes out at 15 times 4, or 60 bytes. On the flip side, the TCP protocol mandates a bare minimum of 5 core rows just to function. So the minimum HLN value has to be 5. And 5 times 4 gives us a mandatory 20-byte base header. So your TCP header can never, ever be smaller than 20 bytes, and it can never be larger than 60 bytes.
All right, let's put it all together. Section 5, Exam Spotlights.
Here is a classic multiple select question for you. Which of the following values can be a valid TCP packet header size in bytes? 15, 20, 30, or 60? I want you to think really carefully about that multiplication rule we just established before I give away the solution.
If you remember the HLN times 4 rule, this question is an absolute breeze. Because the header size has to be calculated by multiplying an integer of words by 4 bytes, valid byte sizes must always, without exception, be multiples of 4. This instantly eliminates 15 and 30 regardless of the minimum and maximum limits we talked about. Both 20 and 60 are multiples of 4, and they neatly fit right into our 20 to 60 byte limit rule, making them the correct answers.
And this brings us to our final calculation piece, the TCP options field. If the absolute maximum header is 60 bytes, and our mandatory base header takes up 20 bytes, what actually happens to the remaining space? Well, we can subtract the 5 base words from the 15 maximum words, which leaves us with exactly 10 words. 10 words times 4 bytes means that the remaining variable space, up to 40 bytes, is entirely dedicated to TCP options. This allows the protocol to scale dynamically based on whatever the network needs without breaking the core structure.
So, we've cracked the N plus M operational logic, we've decoded the exponential math of selective repeat ARQ, and we've totally mastered the HLEN word-to-byte formulas. But I want to leave you with this final, kind of wild thought to ponder. Every single message you send, every streaming video you watch, every web page you load, it all relies on these exact formulas running flawlessly in the background. Think about how incredible it is that manipulating these precise, seemingly dry mathematical limits, sometimes within just a tiny 4-bit header, is the exact structural key that prevents the chaotic global internet from collapsing in on itself. Thank you so much for learning with me today on The Explainer. Keep analyzing, keep calculating, and I'll catch you next time.